Hi, college algebra kids. This is your very last section in the entire class. So after we finish this, you have all the material. Then all we have to do is take test 4 and take our final exam, and you're done. So please, please, please be keeping up with your My Math Lab assignments. Section 4-5 is very short. It's only 2 pages. And the actual My Math Lab assignment is very short. There's not a lot of questions. However, they are word problems. Now, don't freak out on me because we are doing the My Math Lab problems. Notice I don't even have a lesson on here because all we're gonna do is go through and do each problem that you are gonna encounter in My Math Lab. So you're gonna have every single problem. All you have to do is make sure you're following along with the video or the packet or the notes or however it is you're doing these when you go to work on your My Math Lab. Okay, so the reason they're important is because we've been solving exponential equations, and exponential equations can also be used as models to help in engineering and in science and in city planning, and they're just extremely important in the real world. And so the department wants to make sure that you're comfortable using them. So here we go. We have an exponential model right here. Question 1. It describes the population of a U.S. state. Anytime you have city planners or civil engineers that are trying to help design your city or make sure that you have what you need in your town, they have to be able to project future growth. They have to know how many people they expect to be living in your town in the future, so that they plan accordingly for electricity and utilities and roads and parks and schools and all that good stuff. And so we use exponential models in order to do that. So this is an exponential model. So we have A, which is going to be the future amount, the projected population in millions of this state. We have this value, this 947.9, which is going to be what we call the original population. So this might be currently how many people are in the town, okay? Then we have E, remember that's a button on your calculator, raised to some kind of constant we call K. And this is a value that will always be given to you because it involves a lot of information that has to come from the town or the city, that sort of thing. Times T, which is some amount of years that have passed. And in this case, T is years after 2003, okay? So, first question is, what was the population of the state in 2003? Okay, well, T is years after. Well, we don't want to talk about after, we want to talk about in 2003. 2 ways to do this. Number 1, we can just take this little number right here because I already told you this is the population currently, or in when this model was based, or 2003. So that actually is going to be your answer. But if you weren't sure about that, we could take the fact that T is years after 2003. We want to know in 2003, so no years have passed after 2003. So we can write over this equation and we can put in a 0 for T. There we go. Now, anything times 0 is, of course, 0. Anything raised to the 0 power is, of course, 1. And so that's how we would come up with this answer. And again, it's in millions because that's what we're dealing with. Well, I should have just said million, huh? And there we go. Okay. All right, now B, unfortunately, has a mistake in it. I'm going to have to go back and correct. This should not be 253 million. That doesn't make any sense. We're already at 947.9 million. this should be 978 million. So I need to go back and fix that on my packets. I need to fix that in my notes. I just discovered that, so I'm sorry about that. Okay, so next question says, when will the state or the population of the state reach this? So this is A. This is the projected population. Round to the nearest year if needed. Okay, so we have A in this case. We're solving for T. So I'm going to put 978, I don't have to put million because it's understood we're in millions, equals 947.9, again that's millions, times e to the 0.022 t. Okay, we're solving for t. All right, well, this is an exponential equation. Here's my exponential term, but I need it alone. I need to isolate it. So I'm going to divide each side by 947.9. There we go. This is going to give us a nice little 1.0314 equals e to the 0.022 t. Okay, this is the part when solving for the exponential equation where we have to take the log of both sides. Well, being that I have a base of e right here, rather than take the log of each side, let's take the natural log of each side because that's going to come in handy for us. So we're going to take the natural log of each side, and we already know that the secret base of the natural log is e, which is the same as this base. So this is going to cancel. We're going to have the ln of 1.0314 on the left and 0.022 t on the right. Make sure we can see, okay? All right, well, we're solving for t, so we're going to divide by this little coefficient over here, and then we're going to need our calculator. Okay, here we go. So I'm going to put in ln, oh, these are going to go away, of 1.0314 divided by 0.022. And look at there, I get 1.4. 1.41. I'm just going to leave it at 1.4. Okay, now this told me to round to the nearest year if needed. Okay, this is not a year. But remember, T is years after 2003. All right, well, first of all, we want to round up. We always want to round up when it comes to this city planning. So we're going to take that 1.4 and we're going to round up to T. Now, I know in math, he's supposed to round down to 1, right? This 4 is not going to push him up to a 2. But whenever you're doing statistics, whenever you're doing these planning, projected population situations, you always round up, okay? Now, this is years after 2003, okay? So 2 years after 2003, what year would that be? Well, it would be 2003 plus 2. We're looking at the year 2005, and that would be our answer, okay? So you're going to get a value for t, you're going to round it up no matter what it is to the next whole number, and you're going to add that to 2003 because that's how t was defined. Okay, next, this says the exponential models that you see over here describe the population of the indicated country. Okay, so country 1, 2, so on. Okay, here's the initial populations of each country, E. Here's that special little constant we call K, and here's T. Okay, so it describes the population of the indicated country A in millions, T years after 2006. Which country has the greatest growth rate? Okay, the growth rate is K. The growth rate is this little decimal next to t, because if we were to look at, before the numbers are placed in, if we were to look at what this formula really looks like, this is it. This is the population projection that we're talking about. This is the original population or the current population. This AO, that's one term. E's in your calculator. K is the growth rate. T is years after 2006. So all you're looking at for each one of these is this little decimal here. And you want to know the one that has the biggest growth rate. So you go through here and find the number that's the biggest. Okay, well, the biggest number is 0.025. Which country has that? Country 2. Country 2 has the largest growth rate because its K is 0.025. Okay, so that's the country that has the largest growth rate. All right, next, by what percentage is the population of that country increasing each year? Well, this is our growth rate. We're going to turn it into a percentage. How do you do that? You multiply it by 100%, and you get 2.5%. So that's how you do it. This is the answer to the first question. This is the answer to the second question. So these are not hard problems, but they are confusing if you're trying to figure it out on your own, especially if you have the wrong number. Okay, here we go. Third example. If the population of a country in 2003 was 38.4 million, okay, and the projected population in 2024, that's a big difference in time, is 66.9 million, what is the projected growth rate K? Okay, so it gives us the same model that we were talking about, right? This is A sub 0, or A of 0. This is the original population. This is regular A. It's the projected population. E is in your calculator. K we're solving for. Now we just need T. So we need to know how many years have passed. Well, we're talking about 2024 minus 2003. We're talking about 21 years. That is going to be T, because T is going to be always how many years past this original information you had. Okay, so here we go. We're going to fill in what we have. A, we said, is this the largest number because it's projected to grow, equals the smaller number. Remember, these are in millions. That's the original population, times E to the K, we don't know K, times T, which is 21. There we go. So now we're solving for K, which is that growth rate, right? We're trying to figure out what it's going to be. We expect it to be a decimal. They always are. If it's positive, the country is growing. If it's negative, the population is shrinking. Okay, so here we go. We are going to divide by 38.4 because we want to get this exponential term by itself. This is going to give us 1.742 equals E to the 21K. We had K times 21. I just wrote it over as 21K. Okay, now we have an exponential equation that's been isolated. Now we need to take the log of both sides. But again, since I'm using E, I'm going to take the natural log of both sides. There we go. We know this secretly has a little base of E down here. We know this cancels. It's going to leave us with the natural log of 1.742 equals 21k. We're going to divide both sides by 21, and that is going to give us k. Let's try putting that in our calculator. Okay, here we go. We're going to have the natural log, these cancel, of 1.742, and we're going to divide by 21. This is our k. All right, I don't think it told us how many decimal places to go out, so I'll just go out 2. And I'll say k is 0.03. There we go. All right, the very last question down here says, now write the completed exponential growth model, that's this guy here, leaving t as the number of years. So it wants us to leave the letter t, but fill in everything else. Okay, we can do that. We're gonna leave A alone, okay, because you always leave A. We're gonna put in the original, then we're gonna have E to this K value times T. This is the growth rate. It looks a whole lot like this one did up here, right? So we're all ready to use it. We have everything we need to try to find a projection in the future, okay? All right, so see, they're not too bad. They're really not. They just, they require some explanation, and I feel bad because we're not doing them together in class, so we gotta make sure that we get these handled here together. All right, very last page, 3 more. All right, well, here's a blast from the past. Look at this guy up here. Find out how long it takes a $3,300 investment to double if it is invested at 7% compounded semi-annually. Oh my goodness. Round to the nearest tenth of a year and use the appropriate formula. Well, hopefully you remember, since this doesn't say continuous compounding, this is our formula. There we go. Okay, so let's see what we know. 3,300 is our principal amount. 7% we're going to change to 0.07. That's our rate. Semi-annually gives our N, which is going to be 2. Okay, that leaves us with T. We don't know. We're solving for T. Then we're going to need an A. What does it want our final amount to be? It wants us to double this, which means 3,300 times 2, 6,600. All right, here we go. We're going to put in 6,600 for A. We're going to have 3,300 for P, 1 plus 0.07 over 2 times 2T. Okay, let's kind of make this a little more friendly here. First of all, I'm going to get rid of this 3,300. I'm going to divide both sides by it. Okay, that's going to be a 2 equals, okay, and then I'm going to do this all at once in my calculator. So here we go. I'm going to do 0.07 divided by 2, and I'm going to add 1 to it, 1.035. Okay, 1.035, and this whole thing is being raised to the 2t. All right, well, we simplified it. Look what else we did. We have an exponential equation. So we can take regular log or the ln. So I'm going to go ahead and take natural log. That's just how I learned it, so I tend to want to do it. Either one is fine because there's no real preference here in what's going on. Okay, there we go. All right, now I want to get this out of the exponent. So if you remember from our log properties, I can take this power, whether you put a log or a natural log, I can take this power and move it up front as a coefficient. Okay, So I'm now going to have the natural log of 2 equals 2t times the natural log of 1.035. Okay. Now I'm trying to isolate the t here. So I'm going to divide both sides by the ln of 1.035. Okay. So I'm going to have the ln of 2 divided by the ln of 1.035 equals 2t. Okay, let's find this number. It says to round to the nearest tenth of a year. So we're allowed to have some decimals in here. We're going to have ln of 2 divided by ln of 1.035. This gives us 20.149 equals 2t. Now we're going to divide both by 2. 20.149 divided by 2. And I'm going to round this to the nearest tenth of a year. And all it wanted to know was how many years. It's going to take 10.1 years to double our investment at this rate, compounded semi-annually. So it's just some more practice with our exponentials there. Okay, these next two are typically what you have on your final exam. One of these two. They both deal with science. So I know in chemistry you have talked about half-life and decay and that kind of thing, and this has to do with that. So this says an artifact originally had 16 grams of carbon-14 present. Don't get caught up in this. Carbon-14 is just an isotope of carbon. It's just a way to date items, okay? So 16 grams was the original amount. That's the important part. 16 grams was original. The decay model is this. Okay, it looks a whole lot like our population model, right? Here's the original, 16. Our K is negative because we're decaying, and T is years. Okay. This describes the amount of carbon-14, just the amount of this isotope present after T years. Use the model to determine how many grams of this will be present in 5,289 years. There's your T. So you're going to use this formula. You're trying to find how much will be present at this point in this many years. The only thing that you have to put in is T. That's it. So I'm going to take my calculator, clear it out a little. Okay. I'm going to do these exponents. Negative 0.000121 times 5289. That gives me negative 0.639969. Okay. Now I'm going to do E raised to this number, negative 0.639969. Okay. I'm going to round this to 0.5273. And then I'm going to multiply 16 times 0.5273. And my A ends up being 8.44. Okay, now you could have done it completely from here. You could have done E raised to the negative 0.000121 times 5289. And you would have jumped right to here, and you could have skipped this step altogether. Multiply that by 16, and there's the answer right there. So you can make it as many steps or as few steps as you want. But All we know is that in 5,289 years, this is how many grams of carbon-14 will be present. Okay. All right, along those same lines, look what we have. We have a decay formula. We have the original amount of something. We have a decay, because K is negative, and a T. Prehistoric cave paintings were discovered in a cave in France. The paint contained 18% of the original carbon-14. And again, carbon-14, it's just an isotope of carbon that they use to help date things. So don't get caught up in that. The 14 doesn't actually have to do with anything. Don't put that anywhere. All right, this is important because if you notice, they want us to estimate the age of the paintings. So they're asking you to solve for T. Well, I can solve for T, but I have two other values that I don't have numbers for. That's where this little phrase comes in, okay? The paint contained 18% of the original. So the paint we have now is equal to 18%, turn that to a decimal, of the original. Or in other words, A is 0.18 of the original, A of 0. This is the key. Okay, I don't want to circle it because I don't want you to think it's the answer, but this is the key to putting in a number. Okay, so here we go. We're going to use this formula. I'm going to replace A with 0.18 A sub 0. That's what I'm replacing A with. I don't know anything for A of 0, so I leave it alone. E to this decimal, this K, times T. This is going to allow us to divide both sides by A of 0, that original, and look, it goes away. And what we're left with is 0.18 equals E times your amount. Now, we're trying to get T out of here. So I'm trying to solve this exponential equation. I'm going to have to take a log of each side. And since I have an E here, I'm going to take the natural log of each side. Whoops. The natural log of each side. Okay, we know there's secretly a little base of E here. These are going to cancel. We're going to get the natural log of 0.18 equals negative 0.000121 T. We're going to divide both sides by that little negative decimal because we want to get T alone. We're going to take our calculator and we're going to put in, make sure you can see that. There we go. Okay. We're going to put in natural log of 0.18 divided by negative 0.000121. That is that's how old the paintings are. That's the age of the paintings. So we're going to round that to a nice whole number. Remember, always round up. 14,172 years old. That is your T. Wow. Okay, there you go, guys. So sorry I wasn't here to deliver your final material in person. It makes me sad, but I hope you're doing okay. And please call, please text, whatever you need. Email me. You can look right under that instructor information on your Blackboard page. I put my cell phone number there if you need me. And I will get a study guide ready for you, and that'll be the next time you hear my voice. So I will talk to you very soon. Bye-bye.